This video is Note 6, Applications of Trig Graphs and Equations, and we're looking at a Tarzan problem. So we have Tarzan, and he is swinging back and forth on a grapevine. As he swings, he goes back and forth across this riverbank, going alternately over land, that's this part, and over water, that's over here. Jane decides to model mathematically his motion and starts her stopwatch. Let t be the number of seconds the stopwatch reads, and let y be the number of meters Tarzan is from the riverbank. Assume that y varies sinusoidally with t, and that y is positive when Tarzan's over water. So over here, y is going to be positive when he's over the water, and that y is negative when he's over land. So in the land side over here, y will be negative values. It says Jane finds that when t equals 2, Tarzan is at one end of his swing where y is negative 23. And that's right here when t equals 2. He's all the way over the land, which is at negative 23 or 23 meters from the riverbank. She finds that when t equals 5, he is at the other end of his swing, and y is 17. So t equals 5, he's at his further distance out here over the water, which is y equals 17 meters, or 17 meters over the water from the riverbank. We're supposed to sketch the graph of the sinusoidal curve. Whenever I'm sketching a curve and I don't have a graph given, I always start by drawing my y-axis, and then I am going to label that here. So I'm going to label this y, and that is in meters. So I'm going to put that there. I need to know what numbers I need on my y-axis. My smallest y right here is negative 23. So I'm going to want to put that down here at the bottom. And my biggest y is 17 when he's at the other end of his swing. So I'm going to put that up here towards the top. If I now wanted to put my x-axis on there, my x-axis would be right about here, closer to the 17. I'm sorry, it says it the wrong way. It would be closer to the 17 than it would be to the negative 23. Oops, so it's not right smack in the middle between the 17 and the negative 23. It's the actual distance. What I also need to know is where is the middle of my graph. The middle of my graph would be right about here. And we have to figure out what is in the middle between 17 and negative 23. And the difference between 17 and negative 23, 17 minus negative 23 would be 17 plus 23, or 40. So it's a 40-meter difference, which means I need a 20-meter distance to the midline, which would put this right here at negative 3 meters. So I'm going to label that on there as well. I like to have some nice horizontal lines going across here to show me where my marks are. So, well, that's not straight at all, but it corrects it for me. Negative 23 was over land, so I made that line green. 17 is up here over the water. So I'm going to make that line blue just to remind me that this is when I'm over the water and this is when I'm over the land. And then negative 3 would be the midline of my sinusoid. And I'm just drawing that as yellow to make a nice straight spot to deal with. All right, now let's see what we can put on our x-axis. We have two times that we know of, t equals 2 and t equals 5. So I'm just going to start out and make a mark. I'm not exactly sure where to make it, but I'll put one right there for t equals 2. And then I'm going to go a little bit of ways from there, and I'm going to make a second mark, and that is going to be when t equals 5. Now let's plot the actual points that are on my curve. At t equals 2, Tarzan is at negative 23, so I have to be down here at the bottom. And at t equals 5, Tarzan has to be at the other end at positive 17. So that means that in the middle of 2 and 5, I'm going to have to hit the midline right there. Now, I would like to make my x-axis labeled, so I'm going to need to work on some spacing right here. So I have this distance right here between 2 and 5, and that distance is 3 seconds. But that's only half of a sine curve, or cosine. It's going from the bottom to the top, not the full period. So if half of the period is 3 seconds, then I'm going to need to double that to get the full period. So my full period would be 6 seconds. Then I need to know how far apart each of the marks are. Well, that's 1/4 of the period. So a quarter of the period, or a quarter cycle, is 1/4 of 6, and 6/4 is 1.5 or 1.5 seconds. So from 2, I would go up 1.5 seconds to 3.5 seconds would give me the middle. And then I'd go up another 1.5 to get to 5. I can keep going up 1.5 seconds, or I could go down 1.5 seconds. So I'm going to mark my x-axis. So as I said, I went forward. I also went backwards some. You don't have to go backwards. You could go entirely forward. That's fine. I also went ahead and labeled my x-axis that it was t in terms of seconds. All right, so now I can plot the rest of my points. I was at the bottom. I went up to the middle, then up. Now I would be back to the middle again. And then I would be down at the bottom at 8 seconds. At 9.5, I would be back in the middle. At 11, I would be up at the top. I need 2 full cycles. I could keep going to the right if I wanted to, but I'm going to go backwards a little bit. I would be at 0.5. If I went backwards another 1.5 seconds, then that would put me at -1 second. And at -2.5, I would be back in the middle then. Now I need to connect my points with a nice smooth sine curve. So I connect all those dots and I put arrows on both ends to show that I do keep going forever in each direction. Remember, it just said Jane randomly started the stopwatch in the middle of this swinging. All right, part B says to write the equation for Tarzan's distance from the riverbank in terms of t. So we know that this is either a sine or a cosine function. I think it's going to be easier to write it as a cosine function, so I can start at this peak, which I know was 5 because they gave me that data point. So I know I'm going to have something of the form y equals, I'm going to have a number out in front, I'm going to have a cosine, and then I'm going to have a bunch of stuff inside here with a t, right? And then I'm going to have something on the end. So let's see where all these values are going to come from. The first thing that we can look at is where we have shifted our graph. We've shifted the middle of our graph right here to y equals -3 is the midline. That means that in order to move my whole graph down 3, I need to put a subtract 3 on the end of my cosine equation. I can also look at how much I swung over the river or over the land, or what is the amplitude of my curve. So the amplitude was how far I went from the middle to a peak or from the middle to a valley, which we decided was 20. So that 20 is going to go right out here in front to stretch me vertically. Now I need to work on, if I wanted to shift horizontally to this point and my period. So if I'm using this point as my start point, I've shifted horizontally 5 to the right. How do I shift 5 units to the right? I'm going to put some more in here. I would need a t -5 inside my parentheses, and that's going to be inside sort of a double set of parentheses, because the last thing I want to figure out right here is b, my period changer. So I know that 2 pi over b is equal to my period. So if 2 pi over b is equal to the period, then that means that b over 2 pi is going to be, 2 pi over the period is going to be equal to b. So I have my 2 pi over my period, which was 6 seconds. How do I know it's 6 seconds? Again, because half the period was 3 seconds, so double that to get 6 seconds. So 2 pi over 6, when I reduce, is going to be pi over 3. So that means I can sneak a b of pi over 3 in here to my cosine equation. So this is just one cosine equation that I have written. There are lots of equations that I could have written. I'm going to switch over to the second answer page here that has some more of them. So in my curve, I started at this peak point. So that was when I shifted 5 to the right, and that's a positive cosine curve because it's starting at a peak. If I wanted to start 1 to the left, or over here at this point, I also would have been a positive cosine point. If I wanted to start down here at negative 23, then my t would have been positive 2. So I could do a shift of t minus 2 would be a negative cosine graph. I don't usually start with the sine curves, especially when there would be decimals involved. But if I wanted a positive sine curve, I would mostly start here at t is 3.5. So that would be t minus 3.5 for a positive cosine or a positive sine curve. If I wanted to start in the middle on the way down for a sine curve, then I could be a negative sine curve. So any of these red equations would work. There's infinitely many more that would also work. The black equation for cosine here is what I did, thinking that was the easiest. Okay, let's go back to the next part. So for C, it says, how long is Tarzan over the water for a complete swing back and forth? So let's see, when is he over the water? He is over the water, let me go back up here, when I was positive values for y. So he's over the water anytime I am above the x-axis. So for this part right here, I'm over the water. But these are not nice values right here where I cross this x-axis. So I'm going to need technology to help me figure out where they are. I'm going to go over to Desmos and graph this. So my Desmos equation was y equals 20. I need the cosine, and then I'm going to put a parenthesis for my first thing. I want my period. That was pi over 3. If I just type pi, it'll give me a pi. I can type divided by 3, scooch over to get my second set of parentheses. It was t minus 5, but I'm going to have to use x minus 5. Double parentheses for that one, and then there was a minus 3 on the end. And you can see that my graph here is not looking real pretty, but I can go to my wrench and I can look at my graph settings. My x-axis was the time, and in my graph that I did, I went from, like, let's say maybe -3 seconds up to 12-ish seconds. My y-axis was my distance from the riverbank, and I went from -23 meters to 17 meters. So now you can see I have a nice looking graph here that resembles what I had on my paper. I am looking for when I hit the x-axis here. If you were in your calculator, you could graph y equals 0 and find some of these intersection points. But in Desmos, we can just click on them. I have the first time that I crossed the riverbank right here on this bump was at 3.644 seconds. And then I also cross again right there at 6.356. And then this one back here was 0.356. So my first two crossings were right here and right here. I'm calling those T1 and T2 when I wrote them down. So I need to find the difference between them. So the difference between them was 3.2, but remember that was this part of the graph right here. So he was over land during that part. So if I want to find over water would be a 6 for the complete swing minus the part where I was over the land, the 3.2 seconds, to give me 2.7125 seconds over the water. The other thing I could have done is use these two t values and subtract them. But this one was past the first 6 seconds, so I didn't. Again, anytime you're logically finding the distance between those two times, you should be good to go. Okay, it says, where was Tarzan when Jane started the stopwatch? Well, Jane started the stopwatch at t equals 0, which is right here. So I'm going to have to go back to my Desmos, and I have it nice pointed out right there already. It's a y-intercept when t equals 0. My y value is 7. So d equals 7 means he is 7 meters past the riverbank, which means he's over water because it's a positive 7. Question E says, find the least possible value of t for which Tarzan is directly over the riverbank. So going back up here, that was this point right here when I hit 0. And I already found that a second ago. That was my T1 right here. So I just need to rewrite that. That's the first time he's over the riverbank would be when there's a distance of 0. So when d equals 0, that was my 0.3562 seconds. Is the first time he's over the riverbank. So we can do lots of questions with real life trig equations like this. We can do swings or pendulums. We can do bouncing springs. We can go back to Ferris wheels, temperatures, all sorts of things. Anything with circular motion. You'll have lots of practice for different things and investigating them on your practice. Be sure that you're using your calculator because a lot of these are not going to be pretty numbers. They're going to be real life numbers that might have some decimals in there. You can either use your calculator or Desmos, but keep your answers accurate and be sure you put units with everything. Great, thanks.